Welcome to the lecture series on CFD, Part 2. This is lecture 35 on solution methods for free surface flows. This lecture begins with an introduction to approaches for the simulation of free surface flows. Interface tracking approach, in which the computational grid is adapted to the position and shape of the free surface at all times, is described first. Next, interface capturing approach, in which the grid is not adapted to free surface shape, is described. The volume of fluid, called VOF method, which is used in most commercial and public CFD software, is described in detail, including the high-resolution interface capturing scheme. Surface tension effects in free surface flows and how to account for them in VOF methods is the next important topic. Other interface capturing methods are also briefly described. Finally, some illustrative examples of application of described methods are presented. Flows with free surfaces are often encountered in nature and in engineering practice. Often, only liquid flow is of interest, but sometimes the interaction of gas and liquid flow is essential and may be the main reason for the study. Main factors affecting free surface flows are gravity and other body forces and surface tension. In internal flows with fluids of constant density, gravity effects are usually hidden in the pressure term, that is, the solution does not depend on the orientation of the solution domain. See section 1.4 in the book. With free surface flows, gravity and pressure terms need to be separated because of a different variation of hydrostatic pressure within gas and liquid. We shall describe the basis of interface tracking and interface capturing methods with emphasis on volume of fluid methods. Several examples of application with application-specific best practice guidelines will be presented. Two main approaches to simulation of free surface flows will be described. In interface tracking methods, immiscible fluids are separated by a sharp interface, that is, the free surface, which represents a boundary for the solution domain for each phase. These could be two immiscible liquids or liquid and gas. The computational grid is adapted to the interface position and shape and must move and deform with it. In interface capturing methods, immiscible fluids are treated as a single continuum, which is equivalent to the homogeneous two-phase flow model. Only one momentum equation is solved, that is, a single velocity and pressure field are computed. The distribution of the phases is determined by computing the evolution of their volume fractions or another indicator variable. If both phases are present in the same control volume, they have the same velocity, that is, there is no slip between phases. Often one flow contains more than one multiphase regime, making the simulation complicated. An example is shown on the next slide. Let us have a look at an example of a free surface flow. This photograph shows the flow of a hydrofoil near the free surface, mounted on a strut which is fixed to the carriage in a towing tank. When the foil is towed at a constant speed, the free surface above it deforms and may encounter wave breaking phenomena as shown in this photograph. In some areas, the interface between water and air is microscopically sharp, so both interface tracking and interface capturing methods are suitable. In other zones, water and air are mixed, with both air bubbles in water and water droplets in air. The resolution of all details of such a flow is impractical, so additional modeling of the mixed zone may be required. Let us first see how interface tracking methods work. They use a moving, boundary-fitted grid with the free surface treated as a boundary between two fluids. The grid is morphed, that is, deformed, following the motion of the interface. At the free surface, the dynamic interface condition must be satisfied, which requires the balance of forces in normal and tangential direction. Surface tension effects are relevant when curvature is high or when the surface tension coefficient sigma varies along the free surface. This figure shows an infinitesimal part of free surface with the length dl and the local coordinate system tsn at its center. At each edge of the surface element, a surface tension force F sigma equals sigma dl acts. The normal and tangential component of the net force acting on the free surface element ds are given by these two expressions. Here, kappa is the curvature of the free surface, which can be expressed as follows via the radii of curvature in two orthogonal directions, t and s. Often, only the liquid flow is of interest. On the gas side, pressure along free surface is prescribed and the flow is ignored. In addition to pressure, viscous and surface tension forces may also have to be included in the balance of forces. If surface tension is important, a pressure jump across interface, which is proportional to interface curvature, must be accounted for. If surface tension coefficient varies along interface, for example due to temperature or concentration variation, a tangential surface tension force must be considered. This figure shows the balance of forces in y direction for a static droplet. If we cut the droplet by a plane y equals 0, the surface tension force, shown here in red, would act in the negative y direction, amounting to surface tension coefficient times the perimeter, sigma times 2 pi r. Pressure is higher inside droplet than in the air around it. Both are uniformly distributed and act normal to droplet surface. These forces cancel out in x and z direction. The component in y direction, which is balanced by the surface tension force, is equal to the difference in pressure times projection of droplet surface onto the cut plane, that is, inner pressure minus outer pressure times r squared pi. The position of the free surface is determined iteratively by considering the kinematic boundary condition, that is, no flow through the interface, which can be expressed as follows. The prescribed pressure at free surface leads to non-zero mass fluxes through boundary cell faces. When pressure is specified, pressure correction is zero and velocity correction is non-zero. Therefore, the boundary must be displaced to prevent fluid from crossing the interface. If flow on both sides of interface is computed, neither of the two fluids may cross the interface. Usually, the heavy fluid, liquid, controls the motion of the interface. On the other side, no flow through interface is imposed. One such method is described in detail by Muzaferia and Perić in 1997. The free surface is represented as a sharp interface. The grid must adapt to the shape and position of the free surface and also to solid walls. This can be difficult to automate, especially when walls have a complicated shape, for example, some ship hulls. Contact angle at walls can be prescribed as a constraint. See the next slide. Free surface overturning, gas enclosures in liquid, or liquid drops in gas are difficult to simulate using interface tracking methods. Regridding may be necessary from time to time, and poor grid quality resulting from excessive grid deformation may be a problem. This approach is usually used for shallow water flows and flows with a smooth free surface. Where the free surface is in contact with a wall, contact angle needs to be prescribed. We distinguish between two kinds of liquid wall contacts. A hydrophilic wall surface attracts fluid and it spreads, creating a contact angle which is lower than 90 degrees, as shown in this plot. A hydrophobic wall surface repels liquid and it does not spread, creating a contact angle which is greater than 90 degrees, as shown in this plot. One can distinguish between four kinds of contact angles. Static contact angle, when the contact line is not moving. Dynamic advancing contact angle on dry surface, when the contact line is moving forward. Dynamic receding contact angle, when the contact line is moving backward, leaving a wet surface behind if the wall is hydrophilic. And dynamic advancing contact angle on wet surface, when the contact line is moving forward over a wall that was previously wetted. Some commercial CFD codes offer only static contact angle as a parameter. One needs to monitor the wetting of the wall to decide whether the contact line moves forward over a dry or over a wet surface, or whether it is receding. When a wall is moving, the contact angle and the contact line are only apparent. At the microscopic scale, gas entrainment takes place. Consider the flow in a slot coater shown in this plot. Liquid comes in through this slot at a constant flow rate. Part of it flows directly in the direction of motion of the substrate which is being coated, while one part flows backward due to pressure P0 being smaller than the atmospheric pressure, PA. This liquid is picked up by the moving substrate, and at this location we see an apparent contact angle. This plot shows a zoom into the vicinity of the apparent contact line. Due to the no-slip condition at the moving wall, air is carried by the substrate. Moving liquid is also carrying air toward the contact line. Most of this air escapes upward, but a small amount is carried under liquid and it is eventually dissolved in it. This happens at a microscopic scale. Macroscopically, we see an apparent contact line with an apparent contact angle, and this is the angle which we specify in the simulation as the static contact angle on this wall boundary. We now turn to the volume of fluid method, which is the most widely used interface capturing approach. The volume of fluid or VOF method considers a single effective fluid whose properties vary according to volume fraction of individual fluids alpha I, which is defined as the ratio of volume of fluid component I to the total cell volume. The mass conservation equation for fluid I, which is used to compute the volume fraction, is given by this expression. It contains the rate of change term and convection term, and may also contain a source term if phase change takes place. This equation is usually rearranged into an equation in integral form in terms of volume fluxes rather than mass fluxes. The reason is that the variation in volume fluxes is much smaller than in mass fluxes, which increases the robustness of the numerical solution method. For example, if we consider a liquid slug being pushed by the gas flow through a pipe, the volume fluxes at both ends are the same, but mass fluxes differ by a factor of about 1000. The mass conservation equation for the effective fluid is obtained by summing up all component equations and using the condition that the sum of all volume fractions must be unity. The integral form of the mass conservation equation for the effective fluid, which is used to compute the pressure correction, is given by this expression. The last term on the right-hand side accounts for the effects of component density variation, for example, due to compressibility. All properties of the effective fluid are computed according to volume fractions. For example, density is equal to the sum of products of density and volume fraction of each component fluid. In VOF and all other interface capturing methods, the location of the free surface is reconstructed from the distribution of the liquid volume fraction or another indicator variable. To avoid excessive numerical mixing of the phases, that is, to obtain a sharp interface, a special discretization of convection fluxes in the equation for volume fraction alpha is needed. The method must produce a bounded solution, that is, each volume fraction must lie between 0 and 1. In addition, the sum of all volume fractions must be 1 at each control volume. The usual schemes which are used in other conservation equations are either overdiffusive, like the first order upwind scheme, which guarantees a bounded solution, or unbounded, like the central difference scheme. Bounded schemes must fall within a certain region of the normalized variable diagram shown on the next slide. The normalized variables at cell center and phase center are defined by these expressions. This figure shows free control volumes through which the free surface passes. That is, the volume fraction of liquid is smaller than 1 in them. We are looking at the phase F of a control volume centered around node C. The center of the neighbor cell on the downstream side is denoted by D, and the center of the neighbor cell on the upstream side is denoted by U. NF is the unit vector normal to the phase F at its centroid, and gradient alpha is the gradient vector which, by definition, points in the direction normal to the free surface. This figure shows the normalized variable diagram, in which the face value of the normalized variable is plotted against the value at the cell center C. Leonard in 1997 has shown that to ensure that a bounded solution is obtained, the normalized face value has to fall within the shaded triangle. The lower bound is the first order upwind scheme, which means psi f equal psi c, that is, alpha f equal alpha c. The upper bound is the line psi f equal 1, which means that alpha f equal alpha d, which corresponds to the first order downwind approximation. The high resolution interface capturing scheme defines the face value of the normalized variable as indicated by the thick line in the diagram. When the normalized variable at cell center C is negative or greater than 1, the first order upwind scheme is used. For psi c between 0 and 0.5, the face value of the normalized variable is set to twice the value at node C, given by this line. For psi c between 0.5 and 1, the downwind approximation is used. This value is corrected by the local current number according to this formula. Here, CFL-L and CFL-U are scheme parameters. Default values in SimCenter StarCCM Plus software are 0.5 and 1.0. CFL correction estimates which fluid flows across the cell face based on how far the interface will move in one time step. Another correction is introduced to account for the orientation of the interface relative to cell face according to this expression. This correction reduces the tendency of interface to align with the grid. C theta is the scheme parameter. Default value in SimCenter StarCCM Plus software is 0.05. Experience has shown that in simulations of free surface wave propagation, a value between 0.1 and 0.2 works better. These figures show how the orientation of the interface affects the choice of interpolation to determine the convected value of the volume fraction through the face K. If the free surface is orthogonal to the cell face, any interpolation gives the correct value, so the first order upwind scheme is good enough. If the free surface is parallel to the cell face, and it is unlikely that the interface will reach the face within one time step, then the downwind approximation is the best, because only the fluid present at the downstream cell will cross the face. If the free surface is inclined to the face, both liquid and gas may be crossing the face in different ratios. The above corrections are introduced to take these situations into account. The convected cell face value of the volume fraction is finally determined from this expression. The face value can also be expressed as a blend of upwind and downwind values because it always lies between them, as expected of a bounded scheme. The blending factor can be obtained from the above expression. It is a function of the normalized face variable and volume fractions at U, C, and D nodes, given by this expression. Let us now look at some application examples. The first example is the simulation of flow over a semi-cylindrical obstacle on the bottom wall of an open channel. The computed distribution of the volume fraction water using SimCenter StarCCM Plus software and the high-resolution interface capturing scheme with default parameters is shown in this plot. Hydrostatic pressure distribution was specified at the inlet boundary according to the prescribed water level. Different solutions can be obtained depending on the downstream conditions. Here we want to obtain the supercritical situation in which the flow accelerates over the obstacle so that the critical condition, depth base fluid number greater than 1, is exceeded. Therefore, a low pressure is specified at outlet to trigger the transition from subcritical to supercritical state. In the supercritical state, downstream condition is not important because information does not propagate in the upstream direction. We see that a sharp interface, one cell thick, is maintained and accurate solution is obtained on a moderately fine grid. The grid does not need to be adapted to the free surface shape, as in the case of interface tracking methods, which will be further discussed in the next slide. These two plots show the initial grid and the free surface shape, and the final solution from a simulation of the same flow studied in the previous slide, but using an interface tracking method and grid morphing. Boundary conditions were the same as in the simulation using the VOF method, see preceding slide. This example shows the importance of the initial grid design for avoiding too large grid deformation. With the block structured grid used here, grid quality has not deteriorated through the adaptation of grid to the shape and position of the free surface. This plot shows the comparison of solutions obtained using interface tracking and interface capturing methods with experimental data. The results from both simulations agree well with experiment and with each other. Interface tracking methods are not suitable for simulations of sloshing in tanks because of wave overturning and splashing at side walls. VOF method works better, but it also encounters problems with interface smearing and dilution of liquid in the gas phase. These plots show the distribution of volume fraction of water from a simulation of sloshing in a tank due to a sinusoidal sway motion, using VOF method in SimCenter Stasis CM+ software and the high-resolution interface capturing scheme. Before the wave overturns for the first time, the interface is sharp, resolved by one cell. However, after the splashing against the tank right wall, the interface becomes smeared. We obtain zones in which a larger group of cells has volume fraction around 0.5. In long-lasting simulations, liquid may dilute by interface smearing into the gas phase, thus increasing its density. If only 0.1% of water is present in control volumes filled by 99.9% with air, the density is doubled compared to air density. This can change sloshing behavior. To prevent liquid dilution into the gas phase, interface sharpening techniques are used in commercial software and OpenFOAM. For example, in SimCenter Stasis CM+, this is done by setting the sharpening factor in the high-resolution interface capturing scheme to a value greater than 0, typically 0.1 to 0.2. The sharpening model is based on anti-diffusion and acts only in cells at the interface. This model is not based on physics laws. It is designed to avoid interface smearing and should be used with care. It is appropriate to activate this feature when simulating violent sloshing and similar phenomena. An example of an application is shown in this video. After splashing, small droplets are created which cannot be resolved by the grid. Without activating the sharpening feature, the small droplets will disappear and dilute in air. With the sharpening feature active, these droplets can be followed until they fall onto a free surface, which leads to more realistic results. Here is a practical advice. One should, when possible, align the grid with free surface and avoid vertical grid coarsening or refinement in the free surface zone. Suppose we want to simulate the free surface flow around a vertical cylinder and the trim grid is locally refined in cylinder vicinity. In one case, we ensure that the grid is aligned with the initial free surface at all grid levels. In the other case, the free surface passes through the centers of the coarsest grid cells, so the volume fraction in them is 0.5. The situation from the right figure should be avoided because the volume fraction from partially filled cells is advected into finer cells and leads to interface smearing. What happens when the flow is simulated with grid like this is shown in the next slide. Here is the result of simulation started with initialization shown in the preceding slide. Initial volume fraction value from this cell, 0.5, feeds into the next two cells, and from here into the next four cells, leading to a highly smeared interface. The smearing cannot be reduced by refining the grid or the time step because the flow is parallel to the free surface. The sharpening feature can only partially help. The best solution is to adapt the grid to the initial free surface or to avoid local grid refinement in vertical direction near the free surface. This increases the cell count but ensures that such problems do not arise. The kinematic condition at the interface is implicitly accounted for by the transport equation for volume fraction. The dynamic condition at the interface may require additional forces in the momentum equations in cells containing free surface, for example, surface tension force. Surface tension forces at the interface, that is, pressure jump in the normal direction if the interface curvature is significant, and shear force in tangential direction if surface tension coefficient is not constant, need to be converted to volumetric forces. The force acting in the direction normal to free surface is proportional to the product of surface tension coefficient sigma, free surface curvature kappa, and the gradient of volume fraction. This expression is known as the continuum surface force and has been derived by Brackbill et al. The force acting in the direction tangential to free surface is proportional to the product of the derivative of surface tension coefficient with respect to the tangential coordinate t and the gradient of volume fraction. T is a unit vector in the direction of coordinate t. Because the gradient of volume fraction is zero away from interface, these terms are only active along the interface, that is, in cells with a volume fraction between 0 and 1. The unit vector normal to the interface is obtained from the gradient of volume fraction by normalizing it with its magnitude. The curvature of the free surface is then obtained from the divergence of the unit vector orthogonal to the interface. When the high-resolution interface capturing scheme described in slides 17 to 20 is used, or a similar method in which the free surface is captured by just one cell, the computation of curvature may be prone to instabilities and produce a non-smooth curvature field, which can cause numerical problems. Usually, a smoothed out copy of the volume fraction field is used to compute the curvature of the interface. The so-called parasitic currents can develop if the fluid moves only slowly or not at all, and the surface tension effects dominate, that is, with a high free surface curvature or surface tension coefficient. This is manifested by high velocities with erratic directions in the vicinity of the free surface, which can cause numerical problems. The reason is that pressure and surface tension force must be in equilibrium when fluid is at rest. The numerical approximations do not guarantee that, because the pressure term is linear and the surface tension term is nonlinear. The curvature kappa is a function of the volume fraction. See previous slide. There are many partial solutions to this problem in literature, but none works in all situations. Here is an example from the simulation of flow in and around an air bubble rising in water, using Simpson Testacea Plus software. The left plot shows the results when the default surface tension treatment is used. The interface is smeared, and the maximum velocity is higher than 11.5 meters per second. The plot on the right shows the result when the optional implicit surface tension treatment is used. The interface is now resolved by one cell, and the maximum velocity is lower than 0.4 meters per second. We can now see flow inside and outside the bubble. If gravity effects in a free surface flow dominate, one needs to account for the change in slope of hydrostatic pressure profile at the interface. This figure shows the pressure variation in z direction across interface. A linear interpolation between pressure values at these two cell centers to determine the value at this face would produce a wrong result, because the slope in pressure variation changes suddenly at the free surface. If shear forces at the interface are important, for example, when the velocity in the gas phase is much higher than in liquid, one needs to account for the change in slope of the parallel velocity component at the interface. A linear interpolation between velocity values at these two cell centers to obtain the velocity at the cell face would produce a wrong result, because the slope in velocity variation changes suddenly at the free surface. The shear stress is the same on air and water side of the interface, but because of a large difference in viscosities, the velocity gradient is much higher in air than in water. The VF method and the high-resolution interface capturing scheme presented in this lecture have been successfully used to solve many problems involving flows with free surfaces. We present here two examples. The first example is the flow around a ship model at relatively low fluid number, 1.42. This flow was a test case at a workshop in Gothenburg in 2010 and has been used many times to test the performance of CFD methods. The hull is a model of a very large crude carrier with a length of about 5.5 meters. The test is very tough because the waves are rather small at this low fluid number. Along this line, parallel to hull, the maximum wave amplitudes are around 5 millimeters, just 1/1000th of hull length. This plot shows the wave pattern on the free surface, while these three plots show wave profiles along these three lines parallel to hull. The agreement with experiment is very good, considering that the variation of free surface elevation is so small. This slide presents the results of prediction of free surface elevation around a container ship model operating at a fluid number of 0.26. The ship model was circa 7.3 meters long, and wave amplitudes along this line are around 30 millimeters, about 6 times higher than in the example from preceding slide. To keep the solution domain smaller, the forcing method described in section 13.6 of the book was used to force the vertical velocity to zero over a certain distance in front and behind the hull. Within the forcing zone, waves are gradually diminished and eventually a flat surface is obtained. This plot shows the wave pattern on the free surface, while these three plots show wave profiles along these three lines parallel to hull. A very good agreement within the unforced zone is obtained with experiment with moderate resources. The computation on a grid with circa 2.1 million cells can be run on a decent desktop within an hour. The main advantage of the VOF method over alternatives is that it is based on the equation for mass conservation. The equation for volume fraction can be extended to more complex physics by adding appropriate models to it. One possibility is to add source terms to model the phase change. Many cavitation models use this approach, including the one described in lecture 39. One could also add turbulent diffusion terms to model non-sharp interfaces, like the zones pointed to in this photograph of ocean wave breaking taken off the Australian coast. Schemes designed to maintain a sharp macroscopic interface between liquid and gas are not appropriate at these zones. Another popular method for computing free surface flows is the so-called level set method. It solves an equation for advection of a variable that represents a signed distance from interface, 0 at interface, positive on one and negative on the other side. Because the level set variable does not appear in any conservation equation, the method is not conservative. Many methods which minimize the effects of non-conservativeness have been published, like reinitialization of the level set function every few time steps. The method also cannot be extended to account for more physics. It simply advects a function that defines the position of an interface. The level set function itself varies smoothly, linearly across interface, which is often praised as an advantage over VOF methods. However, fluid properties are discontinuous at the interface and must be smoothed out by a certain mathematical function, usually over 2 to 3 cells. Many other methods for computing free surface flows have been published. Good results can be obtained with most of them. Here is a summary of this lecture. Interface tracking methods are well suited for flows with a smooth free surface and simple geometries. Wave overturning, trapping of gas bubbles, and ejection of liquid droplets make grid adaptation to free surface difficult. Grid motion along walls of complex shape is also problematic. Interface capturing methods like VOF have no problems with the above situations, but may suffer from parasitic currents when surface tension effects dominate. All methods described here assume that liquid and gas are immiscible and that a sharp interface exists. When this is not the case, as shown in slide 33, accuracy may suffer from numerical smearing of the interface. VOF methods allow extensions to simulate phase change, see lecture 39, and other physics, including modeling of turbulence-induced mixing. See section 13.5 in the book for further details.